The next major topic of this lecture series in lecture 4 was about the island biogeography theory, or IBT, as we can have the abbreviation. And this was based on three assumptions in the first place. First, that there is a kind of relationship between the size and the species numbers of islands. So we said that larger islands will have more species. This is a kind of relationship that is based on observations. So just by looking at numbers, and this is what we were also doing in practice, trying to look at how larger islands in the Aegean or Greek island archipelago would have a larger number of these land snails. And so this is then what we could just in general call this kind of species area relationship. Species area relationship. There is also what is based on the distance between the continent and the number of species. So that will be what is the so-called distance effect. So this is a relationship I just put here. And there was one more third quite special kind of observation that is based on, again, observing some of these specific events, like catastrophic events we can think of as the volcanic eruptions of Krakatoa or other examples that are smaller, or those man-made examples that were created when scientists fumigated some of these islands in the mangrove, which means that in the mangrove we have individual these trees, and so it was relatively easy for scientists to check how species numbers and sets of species would be differing. So what they did is that they covered with a huge canvas individual mangrove trees in the water, and whatever bugs, insects we had here, well, they were all killed. Fumigation means that there was toxic gas in this area covered by the canvas or in this whole box. And so any form of life that was present here has been disappearing. So they killed all the animals. And what they checked again by time is to what extent these sets of species that they originally, before this whole experiment, counted or observed, so how these would change by time, and from other specific individuals of these mangrove trees, of course, different kinds of bugs, different kinds of insects, for example, would move, would disperse and occupy the original plant that we were talking here about. And the interesting thing is that not the same set of species would be present after the fumigation. Some of those would be the same that were present here before the fumigation, but others would be new that perhaps even from further away through dispersal occupy this area. So we see that there will be what we can call a phenomenon called the species turnover. So I'm just going to erase this a little bit and put here species turnover. So in nature we see that species would be changing there is no definite species number in any area. Species would be disappearing, returning, or perhaps only appearing once in the lifetime of a certain area, or once in the history of the planet. Anyhow, I brought here the example of how I feed birds here at home and how I observe different species appearing from time to time or disappearing. So these are then the three observations, and actually we can say that the species turnover is related to the other two observations, so the species area relationship and the kind of distance effect, which says if we have a continent, then different islands, depending on their size and distance from the mainland, so both size and distance here would kind of have a relationship to this kind of species turnover. So we were saying that this whole relationship would have, like in this case, four differences: small and close, large and close, large and distant, and small and distant islands. Now then we had this little chart, the one that I asked you so many times to draw yourself as well. So here we have then kind of two axes on the vertical line, and these would be related to immigration and extinction, and there would be species numbers, the most important on the horizontal axis. So here we say that this is immigration, and this is extinction. And we also said that mainly the immigration will be driven by the opportunity of new species to colonize. So that will be mainly about the distance. Okay, so closer areas, closer islands will have higher immigration rates, whereas the distance islands would have somewhat lower. And it's actually not a point that we need to think about here, because it's a turnover. We think about basically a curve. So what will happen is that individual island species numbers will be moving on a specific curve that belongs to this kind of distance. So then I put here distance. So that is the main driver of immigration. Main driver, of course. Extinction can be, of course, contributing to this one. But extinction is mainly driven by the size factor, because we said if smaller islands we have, there would be more competition. And what we have here then, again, is like, I just make it perfect, different sets of curves here. So what we would have then for immigration is, in each cases, a pool of possible species to colonize. And whenever there are more species present, so if I think of compared to this point, I look at this one, what happens here is that there is a higher number of species already over here. So there will be less and less possible new species that could colonize. So the more species we have already, the smaller chance that we would have newer ones occupy our territory. And at the same time, we can also think of size here. If we have like different kinds of like birds here present in this area, so this is just my schematic drawing of birds. What kind of birds do we have here? Smaller ones, bigger ones. Well, this is a bird. So these would be competing against each other. They would be fighting over resources. Resources here not only means food, but also we can think about like the habitat area itself, the number of possible like nests or safe places available. So these would be competing against each other, which means that the more we have, the higher chance that they would go through extinctions. So here species numbers is growing. Whenever we have here a certain number of species, and there will be a growth, I just put here in species number, we reach a point here where the extinction rate will be higher. So the higher chance, we have more species already, the higher chance that some of them would disappear, go through extinction. So these are basically the two kind of processes that are ongoing: immigration, extinction, driven by distance and size. So what we can do is think about a comparison based on island biogeography theory. So this is just a theory. Think about how individual kind of species numbers would appear depending on size and distance of the islands from the continent or the mainland. You can call it any way, it doesn't really matter. So just to think about an area where there's a larger number of species present. So then, if I just want to simplify this again, draw this, so simple. This is species number, this is the extinction, this is the immigration. Again, this is driven by distance, that one is driven by the size. And here, if I think of these examples again, small, large, small, large, 1, 2, 3, and 4. So just to make it a little bit complicated and that we need to think actually, small island but close. Where will that be? So we know that it's distance, so it's small but close. Distance will be somewhere over here. We have to look at. And a close island will have higher immigration rates. So number 1 and number 3 will be on this curve, and number 2 and number 4 will be on another one. We say that the distance is the same, so they will have the same curve here, 2 and 4. And we can also say that size will matter in case of extinction. So 3 and 4 will have a lower extinction rate. So 3 and 4 over here on this curve. And 1 and 2, since they are the same size, they will be both on this curve over here. So that's why these individual lines would, in their cross points, intersections, draw out the location for 1 over here. So this is 1 point. Here we see 2 over there. So that's for number 2. That will be for 4 and 4. Number 4 and 3 over here. It will be number 3. So let's check in real life. We said that the lowest possible species number in this case will be, for that one over there, small and distant. That's right. The larger species number will belong to 3, which is close and large. Why? Because the immigration rate is high and the extinction rate is low. And approximately the same number could be appearing in an island. We said that's number 3 with the most. So in case of 1 and 4, over here, a small but close, and distant but large island, perhaps the species number will be approximately the same. So that's what we find over here. Very small drawing, we could put it here as well. These are similar. This is then the distant and kind of small, and this is the large and close island, which will have the highest number of species. But we also said that this is dynamic, so these individual points in specific moments in time could be moving on these curves up and down, left to right, but they are dynamic, which means that they are going to return to this theoretically existing point by time. So once there would be like too many species present in an area compared to the natural equilibrium, this equilibrium will be by time restored naturally just by extinctions or lower immigration rates. So I hope this helps a little bit, even though I know that my drawings are quite ugly and quite symbolic.